All right, guys. So we were talking about rational functions, and in class we were talking about how sometimes we'll have a graph that's like this, a rational graph, and that when it's curving, it seems like it's about to hit the x-axis, but it doesn't really quite cross, right? And we kind of see it on both ends here, right? It looks like it's about to hit the y-axis, but it doesn't cross. It's about to hit the y-axis, doesn't cross. Same thing with the x-axis. It looks like it gets really close, but it never crosses. So what ended up happening here is that we have an asymptote on the y-axis, which is like an imaginary line. And what happens is that our graph will never cross these two imaginary lines. So we have one that's going horizontally. We'll call that a horizontal asymptote. And we have one that's going vertically. We'll call that the vertical asymptote. Okay. So I know my graph here drawn is not that great. So I'm going to kind of do it over here on this graph on Desmos, right? So I have the parent function right here. And notice when I have y equals 0, right, we get our horizontal asymptote. All right. Now, our horizontal asymptote, for the most part, it's going to be 1, right? Well, we usually just have one horizontal asymptote, but now I'm going to talk about that a little bit more later on. Now, our vertical asymptote, right, which in this case is also our um, our y-axis, we sometimes have more than one, right? A vertical asymptote, and it has a lot to do with our x-intercepts, right? So like the factors, right? So we've been talking about factors and x-intercepts and x values a lot lately, and we're gonna kind of go a little bit more in depth on that. And usually, before the x intercepts and the x values and where our solutions. And now, when we're doing with rationals and we get into these problems, these x intercepts, these x values, when it equals 0, it's going to be very important because now they're going to be known as our vertical asymptotes. And we're going to see that right now. So usually in the vertical asymptote, you'll have more than one. Horizontal asymptotes, it's one, right? Just like the y-intercept. You only had one y-intercept, you're only going to have one horizontal asymptote. Okay, but in the vertical asymptote, it's kind of like x-intercepts. Sometimes we had one, sometimes we had two, sometimes we had three, and that could happen with the vertical asymptotes because it relates towards the x. Okay, so we talked about transformations, but now let's talk about the vertical asymptotes. And like I said, this is the one that you probably are going to have um, more than one case, right? Now, a couple of the scenarios that we're going to be dealing with. So I don't need this one or this one or this one anymore. Whoops. 2x minus 4. Now, most of the cases that we're dealing with right now on these are going to have just maybe one, possibly two. I'm not going to go too far in having some that have two or three or four vertical asymptotes. We're just going to kind of keep it to the basics, right? Very simple. And this one right here, 2x minus 4, we see it right here. And notice we could actually see a horizontal asymptote as well as our vertical asymptote right here, and we could kind of guess what the answer is going to be. It's going to be anywhere, maybe between, I don't know, 3 and maybe 5, right? Our vertical asymptote, we could even take a wild guess that it's going to be 4, right? So, like we used to write x equals 4. Here, we would see our vertical asymptote right there. Bam, right? And we kind of, well, I should use a different color for the graph so we can kind of see it. Let's use red. And you can kind of see it right there. And notice this graph looks like it's going to get really close, but it won't touch. This line is going to get really close and it will not touch. But the question remains, how do we find this x equals 4? You know, we saw it on the graph. I just kind of guessed on it, right? We kind of just saw it and it was like, oh, it's between 3 and 5. Let's try 4, right? Well, but there's a systematical way of doing this. So what we do is we take the denominator of our rational function. And what we're going to do is we're going to set that equal to 0, and then we're going to solve for x. So for all these problems right here, and that we're looking for the vertical asymptote, we are only looking at the denominator. We are not looking at anything else but the denominator. We'll worry about the horizontal asymptote later. But right now, for the vertical asymptote, we are going to work and figure out so our vertical asymptote. Okay, so we're looking for our vertical asymptote, VA. I'm going to call it VA. Okay, guys, vertical asymptote. Vertical asymptote. Vertical asymptote. Okay, so right now I'm just worried about my vertical asymptote. Now, how do I do this? Well, I take my denominator right here, x minus 2. I set it equal to 0. Okay, then I'm going to solve for x. So plus 2 plus 2, x equals to 2. Okay, I got x equals to 2. So my vertical asymptote is x equals to 2. Now, why is this important? Okay, why is it 2? Well, the reason it's 2, um, and the reason this one up here was 4. Well, let me do the example. The reason that this one up here, my example was 4, is because we have to think about something. Okay, if I was to plug in 4 into my x, I would get 4 minus 4. So that means I would get, on this problem, I would get 2 times 4 over 4 minus 4, which I would get 8 divided by 0. Now, there's a known rule in mathematics, and that rule is you can never, ever, 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 ever divide by 0. Okay? That's a big no-no. Okay? And because it's a big no-no, if we had x equals to 4, that means we're going to have a gap, right? We're going to have a gap. And that's why this asymptote exists, because since we can never divide by 0, and x being 4 would give us 0 on our denominator, that cannot happen. It does not exist. Kind of like that Mean Girls movie. It does not exist, right? It can never happen. And that's why we have this gap. And that's what we're looking for in all of these, actually. We're looking actually for the point where the denominator will equal 0, because that point cannot happen. That input cannot happen, because as we could see, our graph is going to go in two separate directions, and you cannot be in two spots in the universe at the same exact time. Okay, so in essence, all we're looking for is for the denominator to be 0, because that is the point that cannot happen, right? So plus 6, and we get x equals 6. So my vertical asymptote is x equals 6. Excuse me. Right here, same concept, right? We're going to have x plus 3. We're going to set it equal to 0. Minus 3 minus 3. So our x will be negative 3. Okay? Now, we could always use decimals to check our work, right? So let me kind of shut this one off. I have this first one. I'm saying that x is going to be 2, so let's see. I'm going to put a 2 right here. And this line is going to be my horizontal asymptote for number 1. Let's see. I have it written right here, x minus 4, x minus 2, which is this one. All right, okay, bad choice of color again. Give me a second. Let me change this color to, say, a purple. So here we go. Notice the graph gets really close to this line, to this asymptote, but it's never going to touch, right? So that is our vertical asymptote. So that means we did our mathematics right? We did our algebra right. So we found our vertical asymptote, which is right here. And then we still have a horizontal asymptote, but I'm going to show you guys how to get that right now. Okay, so let's just practice a little bit more. Some of the vertical asymptotes are going to be a little bit more complex than others, right? So right here we have this equal to 0. We bring the 12 over. We get 2x equals to 12. Divide by 2. Divide by 2. X gives us 6, right? This one right here, we're going to have the same kind of concept, right? We bring the 3 over. We get 2x equals negative 3. Divide by 2. Divide by 2. X equals to negative 3 over 2. So that's our vertical asymptote, right? So I'm not going to rewrite it up here, but this is our, that's a horrible box, by the way. This is our vertical asymptote. Now, can you have a fraction? Yes, you can. You can have a fraction. So I am going to type that fraction here. So negative 3 divided by 2, right? And that is number 5, which is x 7 plus 2/3. And let's see. Let's see. And lo and behold, look at it. We did our math right. And there you go. You see the graph getting really close to our vertical asymptote, but yet it doesn't touch. Okay. Now look at number 6. Number 6 is one of the ones I want you guys to kind of look at, because when we do solve this one for x, we're going to get two answers, right? So I bring the 4 over, gives me a positive 4. But now to get rid of a square, I have to take a square root, all right? Now remember, when I take a square root, I'm going to have two answers. I'm going to have the positive set, and I'm going to have a negative set. So that means I'm going to have my square root of 4 is just 2, and my square root of 4 would be also negative 2. So on number 6, I am going to have two vertical asymptotes. So I'm actually going to write the two vertical asymptotes, type them in. I'm going to have x minus 2. I'll change this one to x equals to, oops. Okay, what am I doing here? Okay, x equals to 2, enter. X equals to negative 2, enter. I didn't, all right, and then I don't need this one, this one, this one. Which one am I checking? Okay, this one right here. I'm checking this one. So notice I'm going to have these two lines already drawn out. And notice I'm going to graph x plus 1 and x squared minus 4. Again, the colors. Give me a second. Let's try green. And look at that. Look at that. Awesome looking graph, right? So we see this graph. It goes down, doesn't touch that line, gets really close, doesn't touch it, goes down, gets really close, doesn't touch it. So this is a beautiful graph that has two vertical asymptotes, okay? So the vertical asymptote, just again, guys, you're only looking at the denominator. You focus in on the denominator, nothing else but the denominator. You set it equal to 0, solve for x, and that would be your vertical asymptote. Sometimes you're going to have 1, sometimes you might have 2, and sometimes you might even have a fraction. It's a-okay to have multiple vertical asymptotes. It's a-okay to have a fraction as an asymptote, as a vertical asymptote. Do not get discouraged if you get a decimal or a fraction, or if you get 2, okay? Now, hopefully that was pretty clear. And now let us move on to horizontal asymptotes. Okay, so horizontal asymptotes. So I'm going to kind of close this out now. Okay, I want everybody to kind of hone in. Okay, wait, that's pretty good. Let me see. Make my screen a little bit better. All right, I want us to kind of hone in on this little chart right here. Now, this is going to help us figure out our horizontal asymptote. All right. Now, to get our horizontal asymptote, you're going to have three three possible options. Okay, it's not like the vertical asymptote where um, you're actually going to do a lot of algebra. This is more if having to remember the three options. Okay, so there's three categories that we could possibly have. All right, so in any fraction, we have a numerator and we have a denominator. Okay, we have a numerator which is on top, denominator is on bottom. Okay, now there's three options of having a horizontal asymptote. You could have a no horizontal asymptote. I should put no horizontal asymptote as the horizontal asymptote because it's not necessarily no asymptote because we still might have a vertical asymptote. Okay, I should have put no horizontal asymptote. We could have um, we could have an asymptote that's an actual number, right? Something that is like 3 or 4 or -8 or something like that. Or we could have a horizontal asymptote of 0, which is the x-axis. So your three options are going to be the x-axis as the horizontal asymptote, the no asymptote, and then specifically an asymptote that has a number. Okay. Now, each one of these three has a different way of of I guess calculating them. Okay, so this is the way you do. This is the way you figure out whether you have a no asymptote, a no horizontal asymptote. The numerator, so this top number, okay, we're looking at the top numbers. So if the degree is greater, so we're only looking at the degree. If the degree is greater than the degree on the bottom, then we're going to have a no horizontal asymptote. Okay. I call it a no ha, right? So if the degree is greater on the top than on the bottom, then you have no horizontal asymptote. Okay. So what I'm going to do right now is I'm going to kind of zoom out and I want us to kind of, so I'm going to rewrite this down here. We can still have it. I want us just to kind of look at the practice problems. So right here, nope, these two degrees are the same. Oh, look, this one is greater than this one. And since this one's greater, the top is greater, this one would be a no horizontal asymptote. Horizontal asymptote. Forgot the end. Okay. A no horizontal asymptote. So that's like the first one I like to do because that one um, really takes no math, right? I'm just kind of looking. Let me look at the degrees. Let me see. All right, what's the degree of this one? What's the degree of this one? All right, top is greater. Boom, no horizontal asymptote. And if it's not the case, then I know it's going to be one of the other two. Okay. Now, here's the way they're going to trick you guys. They're going to give you a function like this. They might give you something like 4x squared minus 3x, and then they'll put it at the end, 4x to the third. And then they might put 2x to the third plus x squared minus 1, right? And then you might just be stuck, oh, look, this one is not greater. But then you have to remember there's another one back here, right? So just make sure that they're in order. Make sure you're looking at um, the greatest degree of of the equation on the top and on the bottom, the expression on the top and on the bottom. Okay. Okay. Now the next one I like to do is when the degree of the denominator is greater. All right. So what happens when where's the blue? Yeah. Now we saw when the the numerator is greater, the degree. It was a no horizontal asymptote. But what if the denominator is greater, right? What if the denominator is greater? So I'm looking at this one right here. If the denominator is greater, then it's automatically, without a doubt, no questions asked, the horizontal asymptote will be y equals 0 or the x-axis, okay? Without a doubt. So if the numerator is greater, if the degree in the numerator is greater, there's no horizontal asymptote. But if the denominator is greater, then the y equals 0 is your horizontal asymptote. So like right here, notice these are the same. Oh, right here, this one is greater than this one. So on this one, my horizontal asymptote is automatically y equals 0. So no math involved, no algebra involved, but you have to know the rule. Excuse me. So you have to know the rule. So the denominator, the degree of the denominator is greater, then your horizontal asymptote is y equals 0. Now, the other option that could possibly come up is what happens if the degrees are both the same. Well, if the degrees are both the same, you now you take you put your attention to the coefficients of the ones that have the degrees. So I'm only looking at this term because this has the highest degree. This has the highest degree. So since these are the two terms of the highest degree on the top and on the bottom, I now take my coefficients, right? So it's 3 over 5, and that is my horizontal asymptote. So my y will equal to 3 over 5. Okay? So my horizontal asymptote is strictly just the coefficients of the terms that have the highest degrees. Okay? So in this case, these two are the same, right? Right here, this practice problem, these two are the same. So I look at my coefficients. So I get 4 over 2, which that can be reduced to 2. So my horizontal asymptote would be y equals to 2. Okay. This one, guys, it's like super duper important that you just remember the rules, right? Um, in the vertical asymptote, we have to get the denominator set it equal to 0, solve for x. This one is more, it's more case based scenarios, right? We have 3 different types of cases that we could possibly have, and you have to memorize the cases. So please, please, please do yourself a favor, do me a favor, make sure you have this little chart handy when you're doing your homeworks. Make sure you have it handy because this is what you're going to have to refer back to constantly. All right. And if you memorize it, well, you memorize it. Um, I would keep my notes out when I'm doing my homework. Okay. So, uh, last bit of notes today. Now, this I don't believe you're going to have any um, questions on the homework on this, but it's something that goes. Oh man, why can't I move my screen on there? Now I don't believe you're gonna have questions like this on your homework, but this involves this part. This idea is very big, especially like in calculus. So I wanted to kind of go over it. So let me put up. I am going to try. So my graph is. I actually did a pretty good job on the graph. I'm pretty stoked about that graph. But I'm gonna type it up here so we can have it for availability. Minus 3x. And we have 2x minus 3. let me see. So did I write that down right? X squared minus 3x, x squared minus 2x minus 3. And then I had a vertical asymptote of x equals negative 1. And then I had a y equals 1. Okay, so I'm going to try to change these colors real quick to kind of match my graph. And then this one is black. All right. Okay. So this actually looks almost identical to mine. I did a pretty good job, I'm not gonna lie. All right. So what happens now sometimes when we have a rational function is what we call a removable discontinuity. What that is we have this graph, right? So I'm gonna kind of hide the vertical and horizontal asymptotes so you guys can just see the graph. We have this graph here, right? And we know that if we set the bottom, which is the denominator, to 0, we're going to get a vertical asymptote, which will not exist in our points, right? Because we cannot have um, x2 equal to 0. We also know that the degrees play a big part so we can get our y-intercept, which is our horizontal asymptote, correct? So we have a horizontal. But here's the thing. There's another point on this graph that does not exist. And it's actually graphed on here. Well, it looks like it's graphed on here. But when we actually get up close and personal with the graph, we realize that it's not there. Now, we know for a fact our vertical asymptote, since I already wrote it, one of them is negative 1. However, there should be another vertical asymptote, and that should be at x equals 3. So I don't know if you noticed this, but I broke this equation down into the factored forms, and notice there's an x minus 3 here. So that means I'm supposed to have a vertical asymptote at x equals to 3. But look, check out what happens. When I go right here and I go to 3, check out what's going to happen. 275, 2.8. Look when it hits 3. Boom. It says undefined. And notice the graph now has an open circle there. It has an open circle there, which means the graph is not including the point 3. Now, when that happens, guys, that is known as a removable discontinuity. That means the graph is going to be disconnected at that point number 3, well, x equals 3. So that's why it says undefined, that there's no y value attached to that x equals 3. Now, why does this happen? Now, this happens mainly because of what I did over here. Well, actually, everybody does this. Everybody should be doing this. So I have this function, x squared minus 3x, x squared minus 2x minus 3. And what I did is I factored them out. And because right here I have an x minus 3 on the top, along with an x minus 3 on the bottom, these actually nullify each other, right? It's like you're saying 4 divided by 4, that's just 1. Well, then this function turns into this function. But what happens here is that we are actually taking out a point when we're graphing this. And we want to take that point into consideration. We don't want to just kind of like, leave it be. I'm not going to worry about it no more. I canceled it out. No, we can't do that. We always have to account for it. And the way we account for it is we indicate that it is a point of discontinuity. And you'll hear more of this and you'll talk more of this when you get to calculus. Okay. And in calculus, we have these things called limits, kind of like in Mean Girls, right? So in Mean Girls, they talk about the limit does not exist. Now in here, if I was to tell you as x is going to 3, what do you think the answer is going to be. Now we could take a good guess, right? Because right here at 2.95, it is 0.74. And if we go to 3.1, it's 0.756. So we could take a wild guess that when x is 3, it's probably going to be 0.75. That is going to be the answer. And it kind of makes sense because if I was to plug in 3 right here, right, for my x, my y would just be 3 over 4. So we know we could predict that the y is going to be 3 over 4. We could predict that, right? We could literally say, oh, you know what? The y is going to be 0.75, 3 over 4. But if I was to plug in 3 up here into the original equation, we're going to get a 0 down here. So look, we're going to get 3 squared, which is 9, minus 3 squared, 3 times 3, which is also 9. And then 3 squared is 9, minus 6, minus 3, we get 0 over 0. And notice this and this function are supposed to be the same. But it's because we removed that x minus 3 that we don't get the same answer. And because it's 0 over 0, we have this what is known as removable discontinuity. And that's why the x is undefined. Oh, sorry, the y is undefined when x equals 3. Okay. Now, this was just a little bit of extra for you guys. This is strictly for you guys when you guys hit calculus and Cal 1 and Cal 2. All right. So, hope you enjoyed it. Make sure you guys do your homework. It's due Sunday. And I will see you guys Tuesday. Have a good day.